So do we have any questions from previous times? Okay, so let me just like quickly say a few words about what we did in the previous class. We looked at, the last thing that we did, that we looked at what are known as SP2N groups. Okay, so in classical mechanics, right? If you have a system with, say, n degrees of freedom or degrees of, generalized coordinates, then the phase space is 2n dimensional, and a point in the phase space can be thought of as all the QIs and the PIs. And the geometry of the phase space is defined by a two form, omega. So the two form is, a map that takes two of these points on phase space and spits out a number. So it takes, say, V1 and V2, but there's a symmetry that if I apply a matrix on V1 and the same matrix on V2, then this two form is invariant. And the matrices which satisfy this, they are part of what is known as SP2NR group. Okay, so we did very explicitly the SP2, where n is 1. And then I just said that for the general case, the generator of SP2NR has to be this form. Where these are block matrices, n by n block matrices, and B is symmetric and C is symmetric. Okay, so I would like you to kind of verify this for yourself. I'm not setting it as a blue exercise, but this is something that's worth doing. Okay. All right, so this is just closing off what we did last time. And today I want to start with the Heisenberg group. So the Heisenberg group comes about from quantum mechanics. Remember, in quantum mechanics, say if you have a one-dimensional system, one-dimensional system, then your basic variables are x hat and p hat, right? These are the basic observables. And they're represented by Hermitian operators, right? From these you can work out, you can build, say, the Hamiltonian, stuff like that. But one of the assumptions of quantum mechanics is that these basic variables satisfy these commutation relationships. The commutator of X and P is IH bar. And of course, every operator commutes with itself. So we see that this is, if you think of it, if you interpret these matrices as, these operators as matrices, then they form a Lie algebra. So this motivates the definition of the Heisenberg Lie algebra. So the Heisenberg Lie algebra, or the Heisenberg algebra as it is called, consists of 3 generators and what are these 3 generators? These are X, Y, and Z, and they satisfy this commutation relationship. X and Y is Z, and then commutator of X and Y is Z, and then X and Z commutes. So Z is playing the role of IH bar, and Y of Z is also 0. And there is a matrix representation of these things, and they're in terms of 3 by 3 matrices. This is X, and this is Y. And this is Z. Just one second, okay? Let me get that. Yeah, sorry about that. Okay, so these, you should verify that they satisfy the Heisenberg algebra. So, okay, we have a question in the chat. Let me see. Do SP refer to symplectic? Yes. Yeah. Very good, because it's a symplectic manifold, and this is called a symplectic form. This is known as the symplectic form, and there is a theorem which tells us that we can always choose a coordinate system such that the symplectic form has this form, has this form. And that theorem is known as Darboux's theorem. Okay, so coming back to the Heisenberg algebra, so this is the Heisenberg algebra. So so what is a typical element of the Heisenberg group? Okay, so the Heisenberg group is, elements of the Heisenberg group are given by so we're going to generate in the usual way So you take a, we can basically do this, where A, B, C, where A is, so T is one of these generators or linear combination, and A is a real number, okay? So an element of the Heisenberg group, so the Heisenberg group is three-dimensional, right? Because it has three generators. So an element of the Heisenberg group will depend on three real parameters, say A, B, and C. And you can verify that it's going to have this form. It's an upper triangular matrix. Right. And the multiplication rule is, it's just matrix multiplication, but using the matrix multiplication, you can figure out the multiplication rule for the Heisenberg group is ABC times A prime, B prime, C prime is A plus A prime, B plus B prime, and C plus C prime plus AB prime.
So do we have to find that form using series expansion from e to the power at?
Sorry?
The form you wrote, A of ABC, do we have to figure that out by expanding e to the power at using each of the generators?
Yeah. And then it should be obvious that, for an infinitesimal value of A, B, and C, these are the terms, right? So that should be, you just have to verify that these guys satisfy this algebra. And then this is kind of obvious, right? Because if ABC is small, then it's 1 plus A times X, and then B times Y, C times Z, right?
I see. So the generators should not, must not necessarily be a part of the group. Is that the case?
Well, the generators are part of the algebra, right? They're not a group element.
Of the group. Okay.
Yeah, generators are the one plus the generator is a group element.
So that's kind of a
generator
bit different from the generator of the group we started off with in an elementary definition of the group, right?
Right. That's a very good point. For discrete groups, the generator is a group element or a set of group elements which by repeatedly using them, you generate the whole group. But for Lie groups, the generator is something different. The generator is something which, by exponentiation, you get all the other group elements. Okay?
Hi, Jennifer.
I'm in a class, sorry. Yeah. So my friend just stopped by. All right, so any other questions? Okay, so you can verify that for the Heisenberg, from this algebra, that the A inverse of ABC is A minus B minus C plus AB. Okay. So this is actually a non-abelian group. Okay. So this is a non-abelian group. And that should be clear from the fact that the algebra is a non-commutative algebra, right? So it's a non-abelian group, and the center of the group is of this form. And the center is isomorphic to the real. Okay. So therefore, it's a non-compact group as well. Okay, any questions about the Heisenberg group? It's not a very, people talk about the Heisenberg algebra a lot in quantum mechanics, but not the group.
Sir, the non-abelian character isn't quite clear to me because we multiply two elements and addition is commutative. So can we not think of that as the multiplication also being commutative?
Yeah, so if it was, so, you know, yeah, if you it would have been non-abelian if e to the power, say, some element of the Heisenberg algebra and e to the power, say, let's call it x1. But let's not use x because x is one of the, say, e to the power, say, say m, and em1 and e to the power m2, right? So if this is equal to, not equal to e to the power m2, e to the power m1, you know, that's when we have something that is non-abelian. So non-abelian groups always give rise to Lie algebras which are non-commutative. Okay. So the Lie algebra of an abelian group is always trivial. And here we see that the Lie algebra is, the other thing you can see is the following. So yeah, I mean, even this multiplication rule shows you that it's non-abelian, because if you switch these two, the order, then this thing becomes A prime B, right?
Oh, sorry,
So
I
we
missed the
see that the,
interference term, yes.
yeah, so that's basically how we know that it's non-abelian, right? Okay, good. Any other questions about the Heisenberg group?
Sir, how does this group act in the quantum mechanics? I mean, it has to be some physical consequences, right?
Yeah, exactly. So that's a very good question. So in quantum mechanics, we have something like called the Hilbert space, right? So Hilbert space is the space where the state vector of the system is a vector space, right? Now, suppose that you have the momentum operator P, and you want to find out, you know, some, well, you can measure it, right? But the momentum operator has another role. Any of the observables, any of the Hermitian operators which are observables have another role, which is by acting, they create unitary operators which act on the Hilbert space corresponding to some physical transformation. So what do I mean by that? So for example, suppose you have a quantum system in your lab. So this is your system, and you move your lab, you translate it by some amount A. Okay, so A is, so I'm taking a one-dimensional system, so A is a translational, is a vector, is a translation vector, right? So that should have some effect on the Hilbert space, which represents the possible states of this quantum system, right? So what would that be? You know that, you know, this is that, you know, if you had a state psi, suppose your system was in some state psi, just a translation of your system should not really change the normalization of the state. because you're actually not like poking it. You're not like bringing together another system so that there's some non-trivial dynamics, right? So you're assuming that this thing should remain unchanged. That means that whatever effect this physical transformation has on the Hilbert space has to be represented by a unitary operator. But here, what is that unitary operator? It turns out that unitary operator, which acts on psi, is and gives you the state of the system after translation. So let's call this 0 and let's call this A, is e to the power plus minus, the sign is not important, acting on psi. Because P is a Hermitian operator, this thing is a unitary operator. Okay? So, and it's not very hard to show that if psi, if I now look at psi in the position representation, so I take my position basis and do an inner product, and if you have done quantum mechanics with me, this is equivalent to saying this is the position eigenstates with the inner product of the state of the system. So this is going to be a function of x. This is what we call the wave function. And so a translation, so if I translate the system to x plus a, it's pretty easy to show that the wave function changes to a new wave function, psi prime of x. Let's call it, instead of psi prime, let's call it psi of a of x, where psi of a of x is related to the old guy by psi of 0 x minus a. Okay, this is just a little bit of thinking, you can show this. And now suppose a is small. If a is small, then I can expand this to x of 0 minus a d of psi d of x at x0 at x, and this is 0. And now I can say, okay, why don't I divide this by, say, IH bar and multiply this by IH bar, and then we can write it as psi 0 of x plus minus some factor of IA by H bar times some momentum operator P acting on psi 0. So as you can see, the infinitesimal, this has the form of 1 plus some parameter IA by H bar. So there should be some H bar here that I forgot, with the momentum operator acting on psi 0. So this is the infinitesimal transformation. And now if you apply it again and again and again, you should get an exponentiation, which is what this form is going to be, right? So we have shown that translation is generated by the momentum operator, okay? So that's an application of the action of the Heisenberg group on the Hilbert space. Okay, Farhan?
Yes, sir, got it.
Okay, any other questions before we move on to the next one?
Sir, how is the Heisenberg group coming here in the translation? I couldn't quite get it.
Yeah, this is basically an element of the Heisenberg group, right?
Oh, okay.
Yeah. It's a unitary representation of the Heisenberg group. And the fact that it's infinite dimensional is important because if you take the matrix representation that I gave, which is these are finite dimensional, there is no unitary representation of there are no unitary representation of a non-compact group. Okay, let me rephrase that. There are no finite dimensional unitary representation of a non-compact Lie group. Let me write that down. That's a very important theorem. I don't think we'll prove, but yeah. There are no finite dimensional unitary representation of non-compact Lie groups. Okay, and the Heisenberg group is a non-compact Lie group, and we know that a wave function is an infinite dimensional matrix. We can think of it as an infinite dimensional matrix. So this is a unitary action because it's a unitary operator, but it's related with the fact that it's unitary is related to the fact that the object that it is acting on is an infinite dimensional matrix, column matrix, and therefore this is an infinite dimensional representation. Okay, that's a bit advanced. I won't go there. Any other questions?